Go. Is there anyone there talking to us? All right. Thank you very much, folks, for being here, and welcome back, my virtual learners. We are at the moment. This is where we have stopped prior to the simulator exercises. Now you were able to ballast your ships. You were able to bring your vessel to this condition. Now, very often we come up with the dilemma that should I enter the air from the top? Should I enter the air from the bottom? Should I enter the air from inert gas from the bottom or the top, or these kind of questions we all have come across. Now, the ideal thing is that rather than diluting and mixing the whole environment, we should keep the environment with a clear interface like that. That could only be possible if we will displace rather than dilute. Then again, the question arises, do you want to displace it from the top or from the bottom, or from the bottom or from the top? Yes, I'm going to give you a small fingertip which will remain on your fingertip for the rest of your life. So, of course, we need to see what is lighter and what is heavier. Normally the heavier always goes down and the lighter stays up. So as I've told you, something on your fingertip. So on our fingertips we have got nail. So what does nail stands for? Nitrogen, air, inert gas, and other LPGs or petroleum gases. So nitrogen is lighter than everything else, so it will always, you will find the nitrogen on the top. Then if we have an air, it will be the second denser. Inert gas is more denser or heavier, and of course LPGs. LPGs are the combination of all gases. So I'm not telling you anything about the methane, which is your which is your LNG. There is a very strange phenomena with methane, that methane is lighter than air, or when it is above minus 100 degrees centigrade, and it is heavier than air when it is below minus 100 degrees centigrade. So of course that 100 degrees centigrade is just a figure which you should remember. So normally we say my nail, which is M stands for methane, and then methane minus 100 degree is more or less equal to air density. So if we are lowering the value for minus 100, then it will go down, otherwise it will go up. So whatever thing is heavier, we introduce it from the top, from the bottom. Like you have seen here, you may be able to see the lines. We are introducing it from the bottom, and it is pushing the lighter gas out from the ventilation line. So let's press on further. So now we are inerting tanks. So what was in the tank? Which you have noticed that in the tanks we have got the air. So if we see what will be the ideal point to put an inert gas? Yes, air is lighter, it will stay up. We will very slowly put inert gas in it, and slowly the inert gas will push out the air. So there is no need for throwing the inert gas with high speed or turbulate it. We will slowly and gradually increase that thing. So inerting tanks, after inerting tanks, we need to inert the pipelines. We do not want, I repeat, we do not want any air in our cargo system, because air can take us into the flammable environment if there is right amount of oxygen and hydrocarbon. So why we are for inerting the pipelines also? To avoid the formation of flammable atmosphere anywhere in the system. And that is the details are written in the IGC code chapter 9. How we do it? Typically with an IG generator, normally on this size of vessel which you are working on, it is about 14,000 cubic meter. You can do it in line cooler or dryer. Oxygen, ideally we should have lowest possible, but it should be at least below 2%. Dew point temperature, we have discussed earlier, should be minus 40 degrees. But we are saying always by displacement. So because of displacement, the displacement take lesser time. Dilution take very long time. Dilution is also a method, but dilution is never a real good process. So it is a layer or piston method in parallel. So technically the heavier gas push off the lighter gas from the ventilation lines, and of course that will change the whole environment. It is exactly feeling like liquid in your tank and taking out the gases inside. So inerting by displacement in the exercise which we will load next, you will load it with very low speed, and about the tanks are 135 cubic meter, and you have a plant of 11,000 cubic meter. Roughly you need about 1.2 atmosphere change. So for example, if you have to change the whole environment of 135 cubic meters, you can understand, multiply it by the 1.25, that is 168,750 cubic meters of environment you need to replace. So of course if we divide it by 11,000, we get about 15 hours 20 minutes time to inert the whole ship. That is a typical requirement. Of course our bunker barge is much smaller than these ships, so we can easily do it in few hours time, the inerting process. And of course the gas oil consumption, say it is 16 tons if we are doing in 15 or 20 minutes, and 1.5 changes if we just change a very small change of 0.25 atmosphere. We decide, okay, we want to do more changing. We have turbulated the tank environment, so now we'll have to do 1.5 times the changes. It becomes suddenly from 135,000 or 168,000 cubics to roughly 202,000 cubics, and the time has increased also. But the biggest thing, we are running those generators on low sulfur diesel oil, which is an expensive commodity. And of course, if they, instead of burning running the generator for 15 hours, 20 minutes, you are running it for 18 hours, rather than burning 16 tons, you are burning 18 tons of fuel, expensive fuel. Your ship owner will not be very happy. So anyway, what we try to do is we try to achieve the targets or the environment. We do not compromise on the safety. So even if this process has to run for 4 days, we will be happily doing it. So entering of IG on top or the bottom of the tank, of course, the IG density, it depends on IG density. If it is heavier than air, then of course use the bottom line. If it is lighter, then you push it from the top and you take it out from the bottom. Okay, so let's press on. This is a dilution method. What we are doing in dilution method is by mixing of inert gas and gas residues. If we throw the air very fast in the tank, it will create an eddies, it will create turbulence, and of course the mixed gases will be vented out. But the problem here is that you need a significant amount of inert gas to replace or to change the environment to safe mode. So of course, let's see how much we are going to consume as compared to the displacement method, where we were using about 16 tons of 16 tons of fuel oil to create 16 tons of gas oil to create in work done in 15 hours 21 minutes, so or 20 minutes. So how much it is going to take? It is going to take multiple times more. Normally it is 5 times the environment. Again, it depends on your tank construction. Some tanks give you the results fairly quickly, and some tanks take more time. Now, because you are working on a spherical model, you can see these are the 35-70 millimeter thicket holes. But did you notice your tank will become more and more thicker when it comes to the equatorial ring? Mind that this is the equatorial ring where the tank is sitting in the socket. Okay, all this space is called hold space. This is normally just a tank cover, which we see from outside of the tank, and tank dome, which has got everything fitted to it. And then of course we have got a drip tray which acts as the secondary barrier. So this is a MoS type spherical tank. This is the layout of a spherical tank. There is one person standing here. You can see how it is, you can understand how big is the tank. And this is the equatorial ring area here, and this is where it takes all the load of the tank is transferring to the ship. Mind that you can see here the people can walk right underneath the tank, very close to the drip tray, to do the inspection. Most of the time, most of the companies, the hold is filled with dry air. But if you have no intention for going in this hold space, then of course it is your choice. You can even inert it like from nitrogen, etc. So how it is done, how these tanks are made, is that they are normally bonded through the different metals bonding process. and they are on a very high heat level. So how these two different layers of metals are joined together through the explosion welding. That explosion welding creates a pressure of 600,000 psi, which normally no hydraulic press or the other presses will not create, and it will also create heat or generate. So what we do is that we use explosives to bombard on it, and of course now the collision point is happening, and this is how we keep on bonding these two plates, the base plate and the top plate. Okay, so and once with the heat and the explosion process, the metal is bonded literally like this. So it could be an aluminum bonding with a steel bonding, or two different metals are bonded. The fluid-like behavior of the metals under high pressure is responsible for creating a wave pattern bonding like in an explosive weld. So this type of materials are used because we need certain type of material in the inner side of the tank, and we want certain type of material on the outside of the tank. So this process we use for creating. Now, in a spherical tank, on the first day I've explained you about the annular spaces. So nitrogen is filled in annular spaces. It allows transport of any leakage of methane to gas detectors. So because that annular space is continuously being recycled with nitrogen, and anything which is coming out of that is sniffed by the gas detectors, and if the gas detector detects, then they can easily tell us that yes, there is a leakage in the system or in the tank. Maintain very dry atmosphere between the tank metal and insulation material, including the wedge space around equatorial ring. Rusting is a very undesired situation. So in most of the cases, normally we try avoid that thing. So this is how we manage to prevent the formation of flammable atmosphere in case the leak happens in the tank. Again, with a small little picture, we are trying to explain you that this is the drip tray. There is a gas detection system in between, and of course annular spaces. The first, of course, is the annular spaces, and this is what is being filled by the nitrogen. And then of course we have got the upper insulation layer, and on top of it, it is just the tank cover or fascia, which can protect us from the weather problems. An interesting photograph of the annular space. Can you see that this is the bottom of your tank? Anything, if the tank leaks, there is an insulation behind it, of course, and then the annular space where the nitrogen is filled will leak into this environment and will automatically come down and drain into these aluminum pans. This is actually called the secondary barrier, because in type C tank, on type B and type C tank, which can sustain certain pressure, we do not have, I repeat, we do not have the secondary barrier. There is only single skin tank, but that single skin tank, if it leaks, of course there is nitrogen in the tank will change to nitrogen and methane, and that will create an alarm of leakage. Then furthermore, this is what it is coming to these drip trays. Drip trays act as a secondary barrier. We will get the alarm, oh yeah, there is something leaking and coming in drip tray, and what we can do, we can immediately pump out that liquid. This thing I'll show you again on the. Now we are talking about the inlet of nitrogen into an annular space. Two orifice plates with their valves fitted at the low to allow N2 supply of approximately 20 cubic meter per hour cool down rate from 4 millimeter orifice and 2 to 3 cubic meter per hour normal sea-going, 2 millimeter. The annular pressure, space pressure rises to 50 millimeter water gauge or 5 millibar or just 0.5 kPa. Okay, there is multiple figures involved here. So 5 millimeter water gauge, then 5 millibar or just 0.5 kilopascal. I think we use mainly the kilopascal. So I think all of you professionals out there and in the class, I believe that it is better to use this 0.5 kPa, 0.5 kPa mark. Outlet of a nitrogen space, I've shown you on the valve. There is a valve B which can be opened from N2 from annular space directly, and valve C to screw down valve opens when annular space pressure reaches 20 millimeter water gauge, and of course maintain low dew point. And of course then we will not enter any of those spaces if there is any leakage. So now we have already talked about the displacement process. Now we are giving you some hard facts about the dilution process. In the dilution process, again we are taking an example of the same ship where we have done we have spent about 16 tons of diesel and we managed to do it, the tank environment, pipelines, etc. in 15 hours, 20 minutes. But here, the same size of ship, but rather than using the displacement method, we will see what will happen if we are going to use the dilution method. So, about gas oil composition, it will take not earlier on, you remember we have 1.25, 1.5 times change, but now we will have to do minimum 3 atmosphere change, which is 405,000 cubic meter. Total time there is 36 hours 50 minutes. Imagine, other than your 15 hours, you are running your IG generator for 37 hours, where the ship chartering rates are very high and the owner wants his ship to be prepared, but you are taking that much of time as the chief officer or the cargo engineer or as the master, then company won't be very happy. So gas oil consumption about 37 tons, 5 atmosphere rather than 3. Of course, if you did not get within 3 atmosphere your changes to environment, then of course you will have to go more, 3.5, 4, 5, 6, whatever. So we are taking an example of 5 atmospheres which are 61 hours 20. So gas oil consumption about 61 ton. So you remember, as compared to a very small gas oil or low sulfur gas oil burning, if you are going to burn it continuously for 61 hours and your vessel cannot be chartered for next 61 hours, then you will really be sweating and you will be throwing things around. So now this is a typical inert gas generator. In the last presentation, we have discussed about this generator, only this part. So that is a very simple, same thing, a burner burning, it is lifting up the gas, and of course it goes to R22 cooling system, oxygen analyzer, and so on. This is the typical IG generator or the IG system, folks. Now, this is our tank. Now, for the first time, we are looking at the membrane tank. So, we are going to do the inerting by the displacement method. So, we have simply started our IG plant or IG generator, push the IG in the line, liquid header, and then we are throwing very slowly. We are pushing it down into the tank, and automatically the light air is going out through the ventilation header. It is worth mentioning because our next exercise is going to be on the membrane tank, few of them. Ventilation header, inert gas header, condensate return line, vapor header return line, liquid return line, etc. So that is the way we were doing it. We are displacing from the bottom line and taking the lighter stuff out from the top. But instead of this, if we just throw the inert gas in here from the top and then let it flow out automatically under pressure to the shore, then it is not a very effective system. Reason being, whatever has been thrown from here will be mixed with the vapor which are already there. Mind that those vapors are your LNG vapors and also your IG vapors, or your air vapor and IG vapors. So that was the method where we are in starting the inert gas generator and do the inerting of the tanks. Folks, now we are what about a 5-minute break when I'll switch off on the another simulator to let you have practice on the starting of inert gas generator, and of course you can experience the starting of inert gas generator and the other bits. So just bear with me for a minute. I'm going to the control room to change system.